Think about motion for a second. Pushing a grocery cart, tossing a ball to a friend, or, well, just sitting perfectly still. It all seems so obvious, right? So intuitive. But just beneath the surface, there's this incredible set of unseen rules that are running the entire show. So let's peel back that curtain.
So, what is it, really? What's the secret sauce that gets things going? And what makes them stop? This is a question that stumps some of the smartest people in history for centuries. And the answer, it turns out, is way more surprising and honestly a lot simpler than you might think.
All right, to get to the right answer, we first have to talk about the wrong one. The one our brains kind of tell us is true every single day. Let's explore our built-in, but let's be honest, deeply flawed idea of physics.
For a long, long time, the thinking was that motion came in two different flavors. First, you had natural motion, this idea that things just, they naturally run out of gas and stop. Then there was violent motion, which meant you needed a constant push or a pull to keep something moving. And it feels right, doesn't it? In our world, which is full of friction, if you stop pushing a box, it stops moving. But this is exactly where our everyday experience hides a much deeper, more fundamental rule.
And that brings us to the great plot twist in the story of physics, all thanks to Sir Isaac Newton. It's a principle we can kind of playfully call the law of cosmic laziness, but you probably know it by its real name: inertia.
So here's the big takeaway. Objects don't naturally want to stop. They naturally want to keep doing whatever it is they're already doing. Inertia is just an object's stubborn refusal to change. If it's sitting still, it wants to stay still. If it's moving, well, it wants to keep on moving. It's really that simple.
Now, this laziness comes in a few different types, which is pretty cool. First up, the inertia of rest. Okay, picture this. You shake a tree branch. The branch moves, but the leaves, thanks to their inertia, try to stay right where they are. That resistance to the sudden change is what snaps them off, and they fall. They were lazy, and it cost them.
Next, we've got the inertia of motion. This is an object's resistance to slowing down or stopping. Think about a long jumper. They don't just stand at the line and jump, right? No way. They sprint down the runway to build up a ton of forward motion. Then, at the moment of the jump, their inertia helps carry them forward through the air. They're literally using cosmic laziness to their advantage.
And oh man, this one perfectly illustrates the final type, inertia of direction. We've all felt this a million times. You're on a bus, it's going straight, and then it takes a sharp left turn. What happens to you? Your body tries to keep going straight ahead. The bus turns, but your inertia doesn't want to, so you feel like you're being thrown to the right. You're not actually being pushed right, you're just trying to keep going on your original path.
Okay, so if objects are so lazy and just resist change, how do we ever change anything? How do we speed things up or slow them down or make them turn? Well, for that, you need a force. And lucky for us, Newton gave us the exact recipe for it in his second law.
All right, that's the official straight out of the textbook definition. It sounds pretty complicated, right? All this talk about rate of change of linear momentum, it's super powerful and precise, but
thankfully for all of us, that dense sentence can be boiled down into one of the most famous and powerful equations in the history of science. And there it is, F equals ma. Force equals mass times acceleration. This is basically the engine of the universe in three little letters. You want to change an object's motion, you want to accelerate it, you need a force. And how much force? Well, it just depends on two things. How heavy the object is, that's the m, and how much you want to speed it up, that's the a. It's the simple, elegant rule for making things happen.
Let's move on to the final law, and you'll see how this all connects. We know objects are lazy, and now we know how to force them to change. But Newton's third law reveals this hidden, just beautiful symmetry in every single one of those interactions.
You've heard this a million times, I know, but have you ever really, really thought about what it means? It means you can't touch something without being touched back. Nothing in the entire universe acts alone. Every single push is also a pull.
This slide might look a little technical, but it shows us one simple, profound truth. Forces are interactions. They are never lonely. They always come in pairs. When you push on a wall, guess what? The wall is pushing back on you at that exact same moment with the exact same amount of force. The universe sees it as a perfectly balanced two-way conversation.
And what's a totally mind-blowing application of this? A rocket in the empty vacuum of space. You'd think there's nothing for it to push against, right? Wrong. The rocket violently throws hot gas out of its engine. That's the action. And in return, that gas pushes the rocket forward with an equal and opposite force. That's the reaction. It literally has to throw a piece of itself away to move forward. How cool is that? So there you have it, 3 laws. Each one is pretty simple on its own, but they build on each other to create the bedrock of how we understand the physical world. Let's do a super quick recap.
Okay, first law. Objects are lazy. They have inertia. Second law. To overcome that laziness and make something accelerate, you need a force, and the recipe is F equals ma. And the third law. Every single force is just one half of an interaction. There's always an equal and opposite reaction. From a game of billiards to the planets orbiting the sun, these 3 simple laws are running the show.
These laws describe the world we live in with incredible accuracy. I mean, they let us build skyscrapers and send robots to Mars. But as we look at things that are very, very fast, like close to the speed of light, or things that are very, very tiny, down at the atomic level, we find that these perfect, elegant rules start to break down. And when they do, they reveal a universe that is even stranger and more wonderful than Newton ever could have dreamed. But that's a story for another explainer.